Hey everybody! Today I've got something interesting to show you, but first, listen to this. Almost sounds like a bell, right? Well, what's so special about that? The cool thing is that we can actually use the sound this part makes to optimize its geometry. For that we'll be using free and open source simulation tools, and today I'm going to show you how it works. Now, before jumping into the simulation topic, let's first talk about what this part is actually used for and why you would like to optimize it. So, this machined aluminum tray is actually part of the open source laptop project that I'm working on. This will be the laptop lid to be exact. Now, if you're a laptop user, you probably know that the lid of a laptop always flexes or bends just a little bit, which is fine, but you have to make sure that it doesn't bend as much so that it could damage the screen or the display panel that will sit inside of the laptop lid. Now, the prototype I have right here is already pretty solid. It really doesn't bend that much. The problem is it's also very heavy, which isn't a good thing if you're designing a thin and light laptop. So the goal for the simulation would be to make this lid as thin and light as possible, while also making sure it doesn't bend more than 2 mm during everyday use. So the fact that we have a prototype available is pretty convenient for us, because now we can take measurements of this prototype and compare them to our simulation results. So we can validate our simulation approach even before jumping into the optimization routine, which will be part of an upcoming video, by the way. So in this video we will only focus on, getting simulation data basically and comparing it to real-world measurements. Alright, speaking of the real-world measurements, this is the highly sophisticated measurement setup we'll be using. It consists only of 2 clamps to mount the lid on a flat surface. Sandwiched in between there is an aluminum profile that just acts as a spacer. The multimeter in the frame is set to continuity mode. One lead is attached to the part that we want to measure, and the other lead is attached to a small steel plate underneath the part. Now, as soon as the digital caliper makes contact with both the steel plate and the aluminum part, the multimeter will let us know with a beep when it's time to read the scale on the caliper. I wanted to show you this measurement setup before jumping into the simulation because we'd like to replicate the setup in our 3D model. I'll show you what I mean by that in just a minute. First, let's take a look at the 3D CAD model of the open source laptop. We are here in my 3D modeling tool of choice. I'm using Spacetime Engineer, but as long as the tool can export step files, it really doesn't matter what you're using. Now, what we are interested in is the laptop lid. Currently you can't see much of it because most of the geometry is hidden behind the cover glass. So let's hide the cover glass real quick so you can see what's going on. So in the top here we can see a small PCB containing the webcam image sensor, 2 microphones, some indicator LEDs and a few touch buttons. Running through the middle here we have a flex PCB that connects the webcam board to the laptop body. These black blocks right here are actually gap fillers made from a very light foam. We need those as a mechanical support for the display panel. The display panel itself, let's just show that real quick, is mounted with 4 screws close to each corner of the laptop lid. As you can imagine, if the lid bends too much, we'll put mechanical stress on the display panel, which of course could damage the panel if you're not careful. That's why you want to calculate how much the lid actually bends. So, to get started, let's grab only the geometry of the lid and drop it into a new file. Now I've created a new file containing only the 3D model of the lid. What we'd like to do now is simplify this geometry as much as possible. This step is not mandatory, but it will definitely save us some time and computational resources later on in the calculation stage. By deleting these details now, we can reduce the size of the mesh that we will create in the next step. On top of that, we can also increase the mesh quality, as we can now delete any features that might lead to very small or distorted elements, for example. One example of a feature that we might want to delete is the chamfer around the edge of the part. This chamfer won't have an impact on the simulation output, but we would have to use very small elements to mesh this short distance right here. Another example of a geometry we want to remove is this radius in the corner of this pocket right here. The mesh elements needed to follow this geometry will become quite distorted, as you can see in the screenshot. Now, deciding which features to delete or leave in the simulation might require a bit of experimentation. Of course, we do not want to simplify the geometry too much and impact the simulation accuracy this way. I have prepared an example of how I've simplified the 3D model of the lid. As you can see, a lot of the details are gone, but as you will see later on, the overall match between the simulation data and the measurement data is still pretty good. Besides simplifying the geometry, I've also added in these round and square pads close to the edge of the model. These pads represent the contact areas of the clamps that are used to mount the laptop lid to the table in the measurement setup I've shown you previously. Now that's basically it for this stage of the preparation process. All that's left to do now is export this model as a 3D step file and jump into the meshing tool. For the meshing tool, I'm using Salom 9.9.0. So let's just go ahead, import our step file. Simulation geometry.step, that's what I've called it. And you can see the file pops up right here in the 3D modeling view. Now let's just rename that to something that makes a bit more sense. I'm gonna call it simulation geometry revision 01 and hit enter. Now all that we have to do in this module here is assign our boundary conditions. For that we just create a group. We'll create two groups. One group is for the boundary condition that we can use to impose a force on. So I'm also going to call it force. Hit apply. And the other boundary conditions is used to tell the solver where we want to fix the 3D model in space. So these boundary conditions will later be handled as a fixed point in 3D space. So we select those two, add them to our selection. Also select those two on the bottom right here and add them to the selection as well, and I'm going to call it fixed. Hit apply and close. Now you can see we have two boundary conditions. Alright, that's all we have to do in the geometry module. Now we can move on to the meshing module. For that we will choose this little icon right here, directly besides the geometry icon. And select mesh, create mesh. Let's call it lid geometry revision 01. And as a meshing algorithm, we want to choose NetGen 1D, 2D, 3D. This algorithm will automatically create a tetrahedral mesh with only a few input parameters needed. Now, tetrahedral meshes are not the most efficient mesh types, but they are easy to generate, especially for more complex geometries. To control the mesh, we click on this little gear icon next to the Hypothesis tab, which will open up a new window where we can input various mesh parameters. To get started, we will only input the maximum and minimum element size we want to have in our mesh. By clicking on the drop-down menu for the mesh fineness, we can also control the growth rate of the mesh. This defines how quickly the mesh element size will grow as a function of distance. If we have a region of very high mesh density, we can control how fast the mesh density decreases into areas with maximum element size, i.e. low mesh density. For the maximum element size, we will use a value of 8 mm. Since the units here are in meters, we will input 0.008. For the minimum element size, we'd like to use 0.5 mm. We will leave the remaining fields with their default values and click on OK. Now you can see a small exclamation mark icon appeared left of the mesh name we've defined. This means the mesh hasn't been computed yet. To change that, we right-click on the mesh name and hit compute. For this geometry, the meshing tool will only take a few seconds to run. After it's done, we get a short summary of the mesh attributes. Before exporting the mesh, we will quickly check if the groups we've defined were correctly transferred. We expand the mesh menu as well as the groups of faces menu, and we should see two items in there. One is called force and the other one is called fixed. These groups were automatically imported from the geometry module. Now that's all looking good, so we can go ahead and right-click Export UNV file. For the simulation itself, we will be using a tool called Elmer FEM. I'm using the GUI version of Elmer 9.0. Now behind the scenes, Elmer is a command line tool that needs only a solver input file to run. Instead of manually setting up that input file, we will let the Elmer GUI take care of that. To open up the mesh we've just exported, we click on File and Open. Now we can go ahead and set up the simulation itself. Usually we'd want to start in the setup menu. Here we can define global parameters like the simulation type, for example steady state or transient. We can define time step sizes, the angular frequency for harmonic simulations, and much more. We don't need to change any of that for our simulation though, so we can close this window and move straight to the solver setup. We can find the available solvers in the model menu under equations. We click add and a new window will appear. Here we can choose from many different solvers that are available per default. We would like to run an elasticity analysis, so we will click on the linear elasticity tab. We would like to solve this equation on the only body we have in our simulation, which is the laptop lid. We will check the box to activate the solver, and we check the box for the body property. We will also rename this equation to elasticity. Now before closing this window, we have to change a few solver settings. We click on Edit Solver Settings and another window will open. We'd like to change the solver method to direct, and we would like to change the procedure to eigenanalysis. This will tell the solver to perform a modal analysis on our geometry. The aluminium part I've shown you in the intro resonates at one of several of its natural eigenfrequencies. If we set up our simulation correctly, we can calculate which tone our geometry will create. We can use this information and compare it to our measurement data to verify our simulation approach. This information will also be valuable later on if we do shock and vibration testing of the laptop design, for example. Now, if these resonant notes are not sufficiently dampened, they can create all sorts of problems. Now, these can range from just amplifying fan noise, for example, to actually damaging the structure of the laptop in high vibration environments. Okay, back to the simulation though. We want to take a look at the first 5 eigenmodes, so we will input this in the eigensystem values field. That's all we will change for now, so let's click on Apply. The last thing we have to change is input this string into the text field. This will tell the solver to convert the mesh we are using into a second order mesh. This option will greatly improve the accuracy of the simulation. Now, we could also create a second order mesh in our meshing tool, but in my experience the simulation runs much more stable if we just let Elmer take care of that. Okay, that's it. So now we just click OK and are finished with the equation setup. With the equation setup done, we only have to input our material properties and the boundary conditions. We'll start with the material by clicking on Model, Material and Add. Now a new window appears that looks pretty similar to the equation setup. Here we can assign materials to different bodies in the simulation. Since we only have one body in our setup, we just check the box right here and click on the Material Library button. Let's add the default aluminium material, but modify some of the parameters to match the 6061 aluminium we are using. We will change the density to 2720 kilograms per cubic meter and the elastic modulus to 68.9 gigapascals. We will also input a Poisson ratio of 0.33. Okay, with that done, we can click OK for the material setup and define our boundary condition. For the modal analysis, we only need to tell the solver where to fix the model in 3D space. We will set up a boundary condition by clicking Model, Boundary Condition and Add. We will switch to the linear elasticity tab and input 0 for all displacement values 1, 2 and 3. 1, 2 and 3 refer to the x, y and z component of the total displacement. By setting each component to 0, we tell the solver that no element in this boundary condition can move in any direction. We will also rename this boundary condition to Fixed and click OK. We haven't yet assigned this boundary condition to our geometry though. For that, we will click on Model, Set Boundary Properties and double click on the surface we want to assign our boundary condition to. Alright, that's it. Let's save our project file and generate the SIF file. After that's done, we can go ahead and run the simulation. We will be running our simulation with the default setup on a single core only. We could also run the simulation in parallel across multiple cores, which is a very handy feature for huge meshes. With this example though, we will be fine with just a single process. Now we just click on Run and observe the results rolling in. The solver log file, which is the window that just opened up after starting the solver, contains the values of our 5 eigenmodes. So let's copy those and convert them into Hertz. Elmer natively outputs these eigenmode values in the angular frequency squared. Converting these to Hertz, we get 39, 78, 187, 233 and 350 Hertz. Now let's take a look what these numbers actually represent. We will use Paraview to visualize the solver output. Elmer FEM has generated a .vtu file that contains all the simulation data assigned to the associated mesh nodes. We can now use Paraview to visualize and even manipulate our model based on these values.
Now, if we open up Paraview and import the VTK files, we won't be seeing much after clicking apply. Now let's change the color representation to one of our eigenvalues. We can also manipulate the color map to show a bit more detail or a bit more contrast. This next visualization is pretty cool, I think. We can warp the geometry based on the displacement vector. On top of that, we can also animate the scaling factor of this filter. This way we can actually visualize how the geometry bends in every eigenmode. The first two eigenmodes are pretty intuitive, I would say. What you are seeing currently is the second eigenmode. In this mode, the two corners are swinging in opposite directions, with the center pivot point staying fixed in space. The first eigenmode also makes a lot of sense intuitively. You can replicate this behavior by placing a ruler on the edge of a table and letting it extend a few centimeters beyond the edge. If you flick the end of the ruler, you will get the same vibration pattern. The remaining eigenmodes get quite a bit more complex. I wasn't able to excite these modes in my test setup, so let's just take a look at them very briefly. Okay, that's enough with the theory. Now let's actually measure something. You already know what the overall setup looks like. We have the laptop lid mounted on the table using two clamps, and we can place weights on the other end of the lid. In the first step, instead of placing weight on the lid, we will tape magnets close to the edge. Well, why, you might ask? We'd like to pick up the vibration pattern in different places on the laptop lid. For that, we need magnets and pancakes. Pancake coils to be exact. We place the pancake coil underneath the magnets and measure the voltage induced by the vibrating magnets with the oscilloscope. The resulting waveform will tell us the vibration frequency at different places on the laptop lid. First, let's take a look at the vibrations in the center of the lid. Looks like we are getting about 36.5 Hz in the middle of the laptop lid. That's within plus minus 10% to the simulation results of 39 Hz we've calculated. We can also explain this lower frequency in our measurement setup with the additional weight added by the magnets. That's already a pretty good match. Now let's move the coil to the corner of the lid and repeat the experiment. Okay, well, that looks a bit odd. That's nowhere near a perfect sine wave, so what's going on here? Let's do an FFT on that signal and look at the frequency contents. Okay, now we're getting somewhere. We are seeing two peaks, one at 36.5 Hz and one at 76 Hz. The second peak at 76 Hz is our second eigenmode that we've calculated to be 78 Hz. The odd waveform we are seeing is the product of two eigenmodes resonating at the same time. We can actually use AT-Spice to replicate this waveform. Here I have two resonance circuits. One is resonating at 39 Hz, representing the first eigenmode, and the other is resonating at 78 Hz for the second eigenmode. I've just added the waveforms together using a programmable voltage source, and the resulting waveform resembles what we can see on the scope. Okay, the first simulation was a success. We have a model and a setup that can reliably calculate the eigenmodes of the lid. But what about calculating the amount the lid bends during everyday use? Well, now that we have a function FEM model, this is only a matter of adding another boundary condition. Before doing so, we have to weigh this highly scientific piece of steel I found in my basement in order to correctly represent that in our simulation. Here we are looking at around 1.1 kilogram. This results in way more torque on the base of the lid than would be the case in everyday use. For our test case though, that doesn't really matter. We would like to verify the simulation, and if the results match up, we can change the values in the simulation to something more reasonable. With a known weight, we can now modify the simulation setup. We will leave the fixed boundary condition as is, but we will add a second boundary that we call force. By changing to the linear elasticity tab, we can apply a normal force value. As the name suggests, this force acts along the normal vector of the surface to which this boundary is applied. In this field, we have to input a pressure in Pascal. We could also assign a force vector along the z-axis. Knowing the surface area of my boundary condition with around 143 mm squared, I need to apply a pressure of roughly 77,000 Pascal to generate a force equivalent to that of a 1.1 kilogram weight. Okay, after running the simulation with these updated values, we get a displacement value of about 1.29 mm on the corners of the 3D model. I'm extracting this data from the corners of the model because this is also the location where I will be measuring the displacement in the measurement setup. Speaking of the measurement setup, I've averaged over 10 measuring results and got a displacement value of 1.41 millimeters. That's 0.12 millimeters off from the simulation data. Considering the less than ideal measurement setup due to the somewhat curved steel plate, these results look pretty good as well. I'm very confident that we can use this FEM model to further optimize the geometry of the lid. As outlined in the beginning, the goal is to make the lid as thin and light as possible by maintaining a total deflection of less than 2 millimeters. In which places we would like to remove material from the laptop lid and in which places we might like to reinforce the part will be a subject of another video. I hope you found this tutorial interesting and that you can make use of the open source simulation tools for your own project. Let me know in the comments if you have any feedback or if you're interested in seeing specific design step of the laptop project in a video format. Thanks for watching.